This is the last part, or at least I hope it's the last part, of this series on computer logic having to do with combinational logic. Combinational means logic that is not clocked in any way. In other words, the inputs are allowed to settle, and then you read the output, and it stays in that state until you're ready to change the inputs again. So what I have chosen as a project is to try to do a circuit that will essentially perform an exclusive OR. Now, an exclusive OR simply means a circuit in which the output is a 1 when the inputs are different. In other words, if you call the inputs A and B, then if A is true but B is false, or A is false and B is true, then you should have an output. Now, I've implemented the circuit using AND NOR gates. I'll explain this in a minute. If it were not for the inversion here, this would be an AND OR realization, as they call it. AND OR is the standard form of logic, combinational logic. It's also sometimes called the sum of products. The reason is the OR gate is the sum gate. The AND gate is the product gate. So this is the sum of two products. Each product is the product of A bar B or A B bar. So to realize this circuit, I had to also have some kind of input that I could change. So I constructed this circuit consisting of two switches, switch A and switch B, which you'll see in a minute on the breadboard. When the switch is in the up position, A is true. In other words, it's tied to VCC, it's a 1. When we switch to the bottom position, it's tied to ground, which is a 0. The same is true of B. Up position is a 1, down position is a 0. So this gives me an A signal and a B signal. Then I have applied those signals to inverter gates. These are 74 LS04s. There are more than two in a package, but this is part of a package. And all they do is invert the signal. So if B is true, B bar is false. If A is true, A bar is false, and vice versa. So I then connected A and A bar and B and B bar into the circuit above. And that resulted in the breadboard that you see here. Now, the switches are on the left, labeled A and B. The chip next to that is the inverter chip. Next to that is the AND chip. In this case, it's a 74 LS08. And by the way, you may notice that I tend to use LS chips. This stands for low power Schottky, partly because they're readily available even today. They don't take much power. You could also do this in CMOS and in other types. But this is a 74 LS08, which is a group of two input AND gates in a package. And then they are feeding a 74 LS02, which is a group of NOR gates. Now we'll talk about this inversion a little bit more, but basically the only reason for the inversion is I want to be able to light an LED when this circuit is putting out true. In other words, when A and B bar or A bar B are true, then I want an LED to light. So let me show you how that works in the actual circuit. The LED that I showed on the schematic connected through a resistor. This is a 1K resistor to the output of this NOR gate is here. On the left are switches A and B, and the LED should light, if this circuit works properly, whenever these switches are different. Right now both switches are to the right. I'm now going to switch B, and you see the LED comes on. Now I'm going to switch A, and you see now A and B are the same, so the LED goes off. And now I'm going to switch B back to it's the opposite, and the LED comes back on. And now I'm going to switch A back to the same as B, and the LED goes off again. So what we have done is effectively created an exclusive OR gate that reads the outputs of these two switches and tells us if they are the same or different. If they're different, the light lights. If they're the same, the light does not light. This circuit, by the way, can also be purchased as an exclusive OR gate, and it's a very common circuit used in computers because it's also what is called a parity checker. I won't get into that, but in essence, the way that this is wired up, it is an even parity detector. In other words, it detects when one or the other of the inputs is a 1. I misspoke. I said even parity. It's an odd parity detector. In other words, if one of these is a 1, then it detects that. If both of them are 0 or both of them are 1, then, in other words, they're the same, then it shows no output. Now, this is an example of a combinational logic design. It's a very simple one, of course. A modern microprocessor has literally millions of these kinds of circuits in it, and they're made up of a slightly different kind of gate. And I'd like to talk about that next. Here is an example of the same circuit. In this case, you do not have to supply the A and B bar. In other words, you don't need the inverters that I used. But what you do need is an extra gate. In other words, instead of 2 gates with their outputs combined into the output gate, you need a 4th gate to provide what is in essence a combination of A and B to supply these 2 inputs. I won't go into the details of this. If you want to go to the Wikipedia website, I think that's where I got this particular diagram. But here it shows the same kind of circuit implemented using a gate called a Nand gate. Nand, just the N at the front, just stands for not. The rest is the AND gate that you've been seeing. So an AND gate with the output inverted, in other words with a circle on the output, is called a NAND gate. This is a realization of the same exclusive or odd parity detector using NAND gates. On the right is an implementation using NOR gates. And notice that these 2 NOR gates are actually just being used as inverters. Their inputs are tied together. So unlike the one on the left, where you only use 4 gates, the one on the right requires 5 gates, 5 NOR gates. I only point this out because the way you make a circuit is not only dependent on the circuit you want to build, but also on what your fundamental building blocks are. Now, to kind of close out this section on combinational logic, what I am going to try to do is show you how you can realize any circuit using either all NAND gates or all NOR gates. So just as here, this circuit was done using all NAND gates, and this circuit was done using all NOR gates, and they are identical circuits, that is, they produce the same output. Now there are some differences. Obviously the amount of power consumed could vary. The time delay from the input to the output could vary, and other things. But in terms of pure combinational logic, they are equivalent. So let's look at how you might be able to prove that you can always realize a circuit using NAND gates if you can realize the same circuit using AND and OR gates. In other words, sum of products form. However, since this video has gotten a little longer than I expected, I'm going to put that one off until the last segment of this series on combinational logic. So I hope you'll enjoy this one, and I hope you'll stay tuned for the final part.